This lecture is titled Atoms, Molecules, and Ions, Oh My, and it is the introduction to AP chemistry. So if you look at this, there's a famous quote by Richard Feynman that says, "If in some cataclysm all scientific knowledge were destroyed and only one sentence passed on to the next generation, what statement would contain the most information in the fewest words?" This is a famous thought experiment that was done and presented to several different scientists. And Richard Feynman's quote was, "I believe it is the atomic hypothesis that all things are made of atoms." In that one sentence, you will see there's an enormous amount of information about the world if just a little imagination and thinking are applied. So, we are going to review our understanding of the atomic models, and we're going to focus on the empirical evidence. One of the biggest differences between a pre-AP and an AP chemistry course is the reliance on, or the understanding that you are going to understand the empirical evidence behind assumptions. So it's not going to be just the Bohr model of the atom, it's why is it the Bohr model of the atom. You need to be able to link the periodic table to the atomic model. You need to understand the general trends on the periodic table. You need to talk about ions and isotopes. You need to be able to calculate average atomic mass and percent abundance. And you need to be able to name different quantities. So these were all things that were covered in first year chemistry, but they were spread out throughout the course of the first semester. Those comprise the first chapter of AP chemistry. So let's take a look at it. First thing is, what do we know about the atoms? There's lots of things we know about the atoms. From a chronological standpoint, the first experiment that we have was Dalton's experiment. And what he did is he mixed various amounts of gases. These orange balloons are represented by hydrogen, and these blue balloons are mixed by oxygen. And what Dalton found was that whenever he mixed different ratios of gases together, he actually came up with a difference in products. This is called the law of multiple proportions that you have here. So if you were to look at it, he predicted that gases would combine to form new products. What he did when he did the experiment was he found that they always gave the same product. For example, when you mix two H's and an O, you get H2O, which we know as water. But when you mix two H's and two O's together, you would get an H2O and you would have a leftover oxygen. And likewise here, you wouldn't get H2O because there's not enough H's in order to make it work. So Dalton figured out from this that there must be small particles that are called atoms. And that's what he represented by a part, or a balloon full of an element was an atom. That all atoms of an element are identical. So there is no difference between this hydrogen atom and this hydrogen atom. That you can't create or divide or destroy atoms. That you can't take an atom and break it in half. You can't take something from nothing and create an atom. And that atoms can combine in whole number ratios to form new substances. And that's what we saw with hydrogen and oxygen becoming H2O. And that's what we have, atoms can be combined, separated, or rearranged. So this was Dalton's theory, and it was good for a long while. But then Thompson did an experiment, and what he did is he said that, okay, I'm going to take these atoms and I'm going to make cathode rays, and I'm going to subjecting a gas to a large voltage. And then what he did is he took these cathode rays and he put them between charged plates. So he had a positive plate here, and he had a negative plate here. And what he saw is when he fired these cathode rays through, they didn't go straight through like you would expect of an atom that's neutral. Instead, what happened is they curled towards the positive plate. So what he knew at this point is he knew that this cathode ray moved towards a positive plate. Now, he already was aware of the fact that opposites attract. You should have learned that in physics, or you should have learned it in chemistry last year, by the opposites attract. And so because of that, he said that you can take an atom and you can divide it into smaller constituents. And he suggested that the cathode ray that he had was a negatively charged particle that he called actually a negative corpuscle of charge, but we now know as the electron. So Thomson was the first one to discover the electron based on the fact that you can deflect cathode rays towards a positive charge. Now, he also knew that the atoms are electrically neutral. If you take just hydrogen gas, it won't move one way or the other. So he knew there must be also a positive charge. And so what he did is he developed his model of the atom, which is referred to as the plum pudding or the chocolate chip cookie model. And it just basically says that everything is positive. Everything is positive everywhere in an atom except where these negative charges, or these little chips, are those negative charges that are spread out throughout the rest, which is positive. This is known as the plum pudding model or the Thomson model, and is based on the fact that you can take these these cathode rays and move them towards a positive plate. Next, you have Millikens Experiment. And what Millikan did is he actually measured the charge and the mass of an electron. So what he did is he used oil drops. And he had this really sophisticated apparatus in which he put oil that was charged, and he charged it using an electric current. He charged oil droplets and suspended them between two charged plates. So you have a negatively charged plate and you have a positively charged plate. So the electron is going, or the charged oil droplet is going to be repelled and then attracted. So it'll actually suspend itself in midair. Okay, gravity is going to be trying to pull it down, but this repulsion is going to put it up. And there's actually a little telescope where you can see where it is, and you can adjust the electric fields until it actually suspends exactly where you want it to be. Now, Millikan already knew Coulomb's law, and he knew that opposites attract. So by being able to manipulate the electric field until he suspended the oil droplet, he was able to figure out, okay, well, here's my mass of my oil droplet, here's the electric field required. Here's my mass of my oil droplet, here's the electric field that's required. And he was able to look and see a pattern in the data. Now, if you were to just look at this data, it doesn't appear that there's any clear pattern. But if you were to get into it and start dividing some numbers around, looking for things like the slope, you would see that there's actually a very clear pattern. Okay, no, this was not his real data, but it's okay because he allegedly faked his data anyway. A lot of people think of these historical scientists as being these perfect people that are wonderful experimentalists and those sorts of things, but in actuality they had flaws and they ran into a lot of the same obstacles that we do today. And it is believed that Millikan faked his data in order to make it fit what he actually believed to be the answer. Okay, Millikan's analysis used Coulomb's law and weight. Okay, if you've taken physics, you should be familiar with something like this, where you have the electrostatic force is equal to the gravitational force. If you haven't taken physics, don't worry about that. This is actually not relevant to the chemistry part of it, but it's just trying to show you kind of how he did this. Okay, you might want to make note that he went ahead and set these two things equal to each other, and this actually allowed him to figure out what the charge of an electron was. Now, we generally recognize the charge of an electron to be 1.6 times 10 to the negative 19th now, which is a little bit different than what he found. But at the same time, he's measuring the charge of a single electron a long time ago. So you've got to give him credit for being able to do that. Next, we have the Geiger-Marsden experiment, which is also sometimes called the Rutherford experiment. What actually happened is Rutherford is actually the professor that's here. He was running a lab, and then Geiger and Marsden were students of his. Actually, Geiger was a postdoc. He was working in his lab, and Marsden was the student. And what they did is they set up this experiment in which they were firing alpha particles. An alpha particle is a helium nucleus. So what it consists of is it consists of 2 protons and 2 neutrons. And so what he did is he took these alpha particles and he fired them at gold foil. Now the gold foil, they were able to make just a few very thin because of the malleability of gold. So as a result of that, they had a layer of gold foil that was just a couple of atoms thick. And what they expected to happen was they expected all of these things to pass straight through. These alpha particles are very high energy particles. And so they likened it to firing a mortar or a rocket at tissue paper. But what they saw was, although a lot of the alpha particles went through and some of them deflected, every once in a while you would see a deflection in which the tissue paper, I say quote unquote tissue paper, the gold foil, actually repelled a mortar or a rocket, which is kind of hard to believe. So you can actually see that the analysis of this data actually led to the belief that there is a positive charge somewhere in the nucleus, and it's got to be a very concentrated charge. Now it also has to be very small. Now the reason why it has to be very small is most of the alpha particles got through. And what you see is, based on this close-up picture, unless an alpha particle comes into direct contact with this nucleus, it's going to go through. So the nucleus has to have the majority of the mass, it's got to be the positive charge, and it's got to be relatively small compared to the size of an atom as a whole. And that led to what we call the Rutherford model of the atom. A lot of times this is referred to the planetary model, and what it says is that there's a positive charge in the nucleus, and that the electrons have to move around the nucleus at a variety of distances. So you'll have one that goes here, and another one that goes here, and another one goes here. And these electrons just kind of move about in circles, just like the planets move about the sun. Then Bohr did his experiment. And in Bohr's experiment, what he did is he filled up these glass tubes with a gas, okay? And he did multiple different gases, so it doesn't really matter what they are. But what he did is he subjected them to a high voltage. Now, what you should know from first year chemistry is that if you subject an atom to a lot of energy, atoms will absorb that energy, and the electron goes up and the electron goes down, and it can produce light. Well, by Bohr's experiment, he subjected these things to lots and lots of light, and he found these light patterns. Okay, these spectral patterns are consistent and unique for every atom. So the spectral pattern for hydrogen is very different from helium, which is very different from lithium, which is very different from argon, and so on and so on and so on. But for each atom, it's the same. Hydrogen always has the same spectral pattern. Helium always has the same spectral pattern. And what's interesting is there are actually very, very few colors produced. So what he determined from this is that the electrons have to have specific energies. So instead of Bohr saying, hey, here's the nucleus and electrons can be wherever, Bohr said it has to be here or here, but not in between. Okay, you cannot have an electron that's there in between. Instead, it's got to be here or here. We now know those circles are called orbitals. And so you have Bohr's model of the atom. It says once again that you've got the positive nucleus in the center, but the electrons orbit the nucleus at specific distances, and these distances right here are called orbitals. And that when you absorb energy, so in other words, whenever this electron absorbs energy, it kicks it up to the next level. And whenever it loses energy, it emits light or something like that, it actually moves down from one orbital to the other. Okay, then we have the Chadwicks Experiment. And the Chadwicks Experiment is something that maybe you're not familiar with. What it actually did is they used the polonium source, which is a source of alpha particles, and they actually used these alpha particles and they fired them at beryllium. And whenever they fired them at beryllium, the beryllium actually lost mass, and so that mass that it lost was in the form of neutrons. Now, they didn't know it was a neutron at the time, but what happened is it would lose mass without really losing atoms, which is kind of interesting. So whenever these neutrons came off, they actually set it up to where they wanted to figure out what these things were. And so they set up something called paraffin wax that's right here. And the paraffin wax, these neutrons collided with the paraffin wax and actually turned into protons and electrons. So at that point, they became the idea that neutrons consist of a proton and an electron kind of combined. And so that gave the essence that it's a neutral particle because you have a positive and a negative that cancel each other out. Okay, so now we know the particle has a mass that's similar to a proton. We know that the particle is capable of being converted into a proton and that it resides in the nucleus. And this is Chadwick right here. Okay, you don't often hear the Chadwick experiment referred to. They just said, oh yeah, and there's neutrons. But neutrons were particularly difficult to detect because they didn't attract to the positive side or the negative side, and they're big. So neutrons were very, very, very hard to discover. Now we come to the model of the atom. So generally what we refer to as the last classical model of the atom is basically this. You have a nucleus which consists of protons and neutrons in the nucleus that are combined using something called the strong nuclear force. Okay, that's the reason why these two positive charges right here can be held together. Okay, so the nucleus is held together by the strong nuclear force. And you have electrons that surround the nucleus with distinct energies that are called orbitals. And they move very, very quickly in a circle because these electrons are attracted towards the positive nucleus because opposites attract. So that's generally what we refer to as the classical models of the atom. Then we have something interesting. There's something called the Davison-Germer experiment. And what they were doing is they were testing what was called de Bruylier's hypothesis. And de Bruylier's hypothesis was just basically this. De Broglie was a graduate student, and he was trying to get his PhD, and he came up with the idea, well, what if we treat electrons like they're waves, just like we treated photons like waves and particles? What if we treat electrons like waves? And he was expecting to see some sort of wave-like pattern. And what they did in the Davison-Germer experiment is they actually fired electrons at a nickel crystal. And when you fire electrons at a crystal, okay, if you were to fire light at a crystal, you see these interesting patterns. Okay, they're called diffraction patterns. And you have this bright spot, and then you have a dark spot, and then you have a bright spot, and then a dark spot, and then a bright spot. And that's because of the wave-like nature of light. Well, it turns out when they did this with electrons at a nickel crystal, they actually figured out that these electrons can scatter as well. Now, what this actually meant was the fact that electrons can't really be treated as particles, but instead are treated as waves. So this is what you see. These are the interference patterns that you see. You see these lines that, hey, here's the electrons, and then in between is not electrons. So this is the interference pattern that says, okay, well, there's got to be something else going on here because the electrons aren't acting quite like particles. Instead, they're acting like waves. And so what they did is this actually took something from this Ernest Schrodinger, his name's hard to say, Schrodinger, came up with this idea that, hey, what if we treat the entire atom like it's a wave? Well, specifically the electrons, but and he came up with this equation. This is a modified version of what is called the standard wave equation in physics. Now, he took this idea of the wave equation and he applied it to the electrons and came up with this equation. You will not cover this equation right here until maybe your second or third year of chemistry/physics in college. Okay, so this is beyond the scope of this class, but you need to know the idea that he treated electrons like waves based on experimental evidence. So that's what we call a quantum model. And the difference between a quantum model and a classical model treats electrons like particles, and a quantum model treats electrons like waves and talks about the position of electrons in terms of probabilities. So you have the Schrodinger model of the atom, and one of the things for the Schrodinger model of the atom is you can't know the position of an electron. You can't say the electron is here and it's going around in a circle. You can't say that. Instead, you say there is a probability ring in which the electron is most likely within this ring right here, and I'm going to call this ring an orbital. That's what they're referring to when they talk about orbitals in the future. They're saying that 90% of the time an electron is existing in this particular part. Now, there's other parts of the time where the electron's right there, or it's outside of the orbital. But instead, the Schrodinger model refers to these orbitals as the 90% mark. So we look at example A1. It says the Bohr model is often referred to as the last of the classical models. Explain the difference between the Schrodinger model and all previous models, and we just did that. It is primarily in how you treat the electron. Is the electron treated as a particle, in which we talk about absolutes? In other words, we say the electron is here, it has a mass of this, it has an energy of this, and it is this far away from the nucleus. Those are the classical models. When we talk about the Schrodinger model or the quantum models, we say, here's the nucleus. The electron is probably over here somewhere. Okay? We don't know exactly where, but it's probably within some sort of ring right here. We don't know exactly where, but 90% of the time that it's right there. We don't know for sure where it is, but we're pretty sure that most of the time it's right there within this margin of error. That's the biggest difference between the models. How would the Bohr model differ? How would the Bohr atomic emission spectrum differ if the Rutherford model was valid? And the key is it isn't. So this is an interesting question because this is kind of an AP level question because it asks you to compare and contrast two models, and you're supposed to say, okay, now if something were different, how would it change? So if you look, the Bohr model of the atom says electrons are here or here, or if you had another one, here. In this case, in the Bohr model of the atom, an electron can go from here to here, or here to here, and produce light, or it can actually go from here to here as well. So there are three colors of light that can be produced. If you had the Rutherford model of the atom says, hey, there's the nucleus, and electrons can be wherever they want to be. So if we want to have an electron here, great. If you want to have an electron here, great. If you want to have an electron here, great. Well, that means that you can have light produced here, 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 here. In fact, you can have every single color of light produced. So if the Rutherford model of the atom were correct, this would show all colors. You would start with purple, and you would see all colors all the way to red. there would be no black spots in which there are no color. Whenever you have the emission spectrum for individual elements, you see much narrower bands like this. Now this is actually a mixture of elements, so don't think of this as evidence of the Rutherford model. This is actually a mixture of elements, which is why you have so many lines. After our introduction to the models of the atom, now we need to talk about the periodic table. And there are two basic periodic tables. Now the first one is organized by Mendeleev and is chronologically the first. What he did is he actually organized the elements by mass and then looked to see where similar chemical properties lined up. And what he did is he left gaps that allowed the prediction of future elements. So he said, okay, well, there should be an element here based on the pattern, but I don't see one yet, so I'm going to leave a gap there. Now, Mendeleev's periodic table actually has some inherent flaws to it, and so we actually use the one that was created by Moseley now. Now, Moseley was based on the idea that the atomic number, or the number of protons, is how you should align the elements, and that when you do that, you get a more consistent pattern for lining up chemical properties. So one of the one that we use now, all the numbers are done by atomic number. Now there's a reason for the shape that you should be familiar with, but if you're not, we'll get into a little bit later. And you should also bookmark ptable.com. That website is going to be used quite often, and it's a good reference for you to have when you're looking at chemical properties. So go ahead and bookmark that in whatever browser you use. So chemical periods. Chemical periods are when all the elements that are in the same row are in the same chemical period. Now, what these refer to whenever they're in the same row means they have similar energies or similar orbitals. So everything in the first row has electrons in the first orbital. Okay? Everything in the second row has electrons in the second orbital. Everything in the third row has electrons that are in the third orbital, and so on and so on and so on. Now, one of the things that you need to be familiar with is the fact that the third orbital consists of this. So this d orbital right here, which we'll get into later, consists of the third order. So when you get to the d level, you have to take those d and move them up one. Now there's a reason why they have it filled like this that we'll talk about a little bit later, but for now you just need to be aware of that. Chemical families refer to elements that are in the same vertical column. And when they're in the same vertical column, they share similar chemical properties. Now, you see all these right here? These refer to the noble gases. They all have similar reactivity and similar properties as far as what they do whenever they're in certain situations. So, the vertical columns have more to do with similar elements than do the rows. Okay, so you need to be familiar with that distinction. Each one of these have different names that we will get into, but we'll get into that a little bit later. Now, one of the things that you need to do is be able to distinguish between an atom and an ion. And basically what an ion is it's where you've taken away or removed electrons so that there is no longer a balance between protons and electrons. Whenever there's an imbalance between protons and electrons, we refer to those things as ions. Specifically, when there are more protons, we call that a cation. And when there are more electrons, we call that an anion. Now, one of the things that's really important for you to realize is that protons don't ever move in a chemical reaction. They can move in nuclear reactions, but we're not going to deal with that in this class. Okay, protons will never move in a chemical reaction. And instead, what happens, either you gain electrons or you lose electrons, and that what determines whether it's a cation or an anion. Okay, whenever we refer to something as ionic notation, we identify the number of protons. Okay, the first thing we need to do is identify the number of protons. So if you were to look at this, I would say we're saying the blue things are the protons. I would say I have 1, 2, 3, 4, 5, 6 protons. Well, when I have 6 protons, I can use that to identify the element. If you were to look at your periodic table, the element on the periodic table with 6 protons is carbon. Okay, the next thing that I would do is I would write the chemical symbol for the element, which I did. And now I need to determine if the object is a cation, where it has a deficit of electrons, or an anion, where it has excess electrons. So I look at the electrons, I say 1, 2, 3, 4. And if you notice, 4 does not equal 6. So instead this thing is going to be a cation because it has more protons than it has electrons. Okay, so what I would do is I would write the surplus of the deficit, and I have 2 extra protons. So this would be the ionic notation for this particular element. You should be able to do that, and you should be able to take the reverse. If I give you this, you should be able to tell me how many protons and electrons there are. Next, we have to name ionic compounds. Whenever we name ionic compounds, what we have to do is we have to identify the cation and write the name of that element. So that's always going to be sodium or potassium, usually things from the left side of the periodic table. Once we've identified the cation, the next thing we need to do is we need to determine if we need to use Roman numerals. Now, we need to use Roman numerals only if, on the periodic table, we're looking at those transition metals. Okay, the transition metals in between, those are the ones in which you have to specify what the charge of the ion is, because they can take numerous options. If something is in group 1 or group 2, or even group 3 or group 4, you don't have to specify the charge, because everything in group 1 has a charge of +1. Everything in group 2 has a charge of +2. Everything in group 13 has a charge of +3. Everything in group 14 has a charge of +4. But these middle elements, you have to specify with a Roman numeral. Then the last thing you need to do is you need to identify the anion. Once you've identified the anion, if it's an element, it is referred to as an ide. So if you were to look, you would have sodium because it's the cation, and you would have chloride because it's the anion, and that's that ide symbol. Now, a lot of times you will see the anion as a polyatomic ion. This ide refers to only if it is an element by itself, like chlorine by itself is chloride, sulfur by itself is sulfide. But there are many polyatomic anions that you need to be familiar with. Now, you've been given a list of those polyatomic anions, and you should be familiar with those so that if I give you a question that says, what is the molar mass of barium hypochlorite, you should be able to say, oh, barium hypochlorite is this, and you should be able to answer the question. Now, whenever we talk about ionization, it's also really important that we talk about ionization energy. This tends to be a question that almost always appears in the AP test in the form of an experimental question. And ionization energy is the energy that's required to remove an electron, and it depends on a couple of things. Okay, it depends on the number of positive charges, it depends on the number of negative charges, and it depends on the distance between the electrons and the nucleus. Now, for those of you who have physics, which I know is not all of you, you should refer to Coulomb's law, F equals kq1 q2 over d squared. Okay, we also briefly touched on this in first year chemistry, but this is the idea of Coulomb's law. It depends on the number of positive charges, it depends on the number of negative charges, and it depends on the distance between them. Now, ionization energy is the energy that is required to take an electron and completely remove it from an atom. There are definite trends in terms of ionization energy, but that's what it means by definition. Okay? Polyatomic ions. You have a list. If you need a copy of the list, go to the class website. Okay, you can download another copy from there. You should be able to write the chemical formula for the following. So it's asking you for calcium bromate. Okay, you should be familiar with the fact that calcium is Ca, bromate is BrO3. Okay, when you have calcium bromate, you have iron 2, and then you have acetate. You should be familiar with acetate. And then finally you have ammonium, which is NH4, and you have a hydroxide. But whenever you write these chemical formulas for these compounds, it's not enough just to write the chemical symbols that represent them. Instead, you have to balance the charges that are associated with them. So you need to know that calcium is +2, and you need to know that bromate is -1. So in order to get these charges to balance, I need twice as many of these to get the charge to neutral. So calcium bromate is actually CaBrO3, but then that bromate is in parentheses, and there are 2 of them. Iron 2 acetate, oh, I didn't finish acetate, did I? I tend to write acetate as CH3COO, which is actually the same thing as, I think on the list it's C2H3O2, which is the same thing, but I tend to write it this way just because that's what you tend to see in organic chemistry. So acetate actually has a charge of -1, and iron can have any charge. The fact that it has a Roman numeral 2 makes it that it is +2. Now, one of the common misconceptions that people have is they automatically go iron 2. That is not the case. Remember, this Roman numeral refers to the charge, not the number of irons. So you would actually have iron, and then you'd have CH3 COO parentheses 2. The last one you have is ammonium hydroxide, and ammonium is NH4 plus. It is the only positive polyatomic cation that you need to remember. And you have hydroxide, which is OH minus, so the answer is just NH4OH. Now, you cannot take this thing and rearrange it and say, I want to call it NH5O. You can't do that. So you need to make sure that you keep the cation and the anion separate. Next, this is name the following. So you want to do the same thing, but from the opposite side. If you're given the chemical formula, remember the cation comes first. So if you look at that, that's barium. If you look at this, it's copper. If you look at this, this is ammonium. A couple of things we know right off the bat. Ammonium is a polyatomic ion, so it doesn't need to specify any sort of charge. Barium is in group 2, so it doesn't need to specify any sort of charge. But copper is a transition metal. So because it's a transition metal, I'm going to need to specify what the charge of copper is. Now if you look at this, in order to do that, I need to know what the charge of sulfate is, because I have one copper to balance out one sulfate. Well, sulfate has a charge of -2, so that means copper has to have a charge of +2. So I'd write copper 2, and then I'd write sulfate. I'd write barium. Barium's +2, so I don't need to worry about that. And this right here is oxalate. And then ammonium, and then this right here is cyanide. So it is really important that you actually memorize these polyatomic ions so that you can name them, so that you can pull the name out and turn it into a chemical formula. That is going to be a given. You have to know how to do that to answer questions for the rest of the year. Frederick Soddy worked with Rutherford to study the transmutation of elements, and that's where an element turns from like helium into hydrogen. He was actually the first one to prove that uranium could actually become radium. So this transmutation of elements actually has a lot of historical origin in what we call alchemy, in which people try to turn different things into gold. But that's the historical origin. We do know that there is some sort of benefit, or it can actually be done with certain radioactive elements. So when he figured out that you have radium, it turns out that radium can have two distinct masses, even though they have identical chemical properties. Now, people automatically thought, okay, well, there's two different masses with the same property, so it just must be two elements. But it turns out that they were identical properties. And so in an extension of Thompson's experiment with neon, so instead of using cathode rays, they just used neon, they actually found out that whenever you charge neon, there was a couple of things that you couldn't understand. So whenever you did this, you would deflect it towards the positive plate. So I have a neon atom and I make it a negative charge. And how I do that is I just put it in a negative current, I attach a battery to it, it becomes negatively charged, and I shoot it between these plates. Well, when I shoot it between these plates, it should curve towards the positive plate. And it does. But what you notice is you get two distinct lines. There's a line right here and there's a line right there. Now the question is why are there two distinct lines if all other atoms are equal? And so this was kind of an interesting, what does this mean? Because you have neon that has identical properties, but there's two different lines whenever it moves through Thompson's experiment. And what actually that was evidence for isotopes. And isotopes refer to atoms or elements that are the exact same number of protons, the same number of electrons. So in terms of reactivity, they're the exact same, but they have different number of neutrons. Now, neutrons, remember, are neutral particles, so they don't actually affect the reactivity. So what you see right here is we write it in hyphen notation. This is helium. The reason why I know it's helium is because it has two protons. Okay? I know that it's not charged because there are two electrons to cancel out the two heliums. But there's still a difference between these two elements. So how I need to specify that is I would say this is He4 and He3 based on the atomic mass. This particle has this atom has 4 particles in the nucleus. This one has only 3. So this is determined by what's called the atomic mass. If you have 2 protons and a neutron, your atomic mass is 3. If you have 2 protons and 2 neutrons, your atomic mass is 4. Now the reason why electrons are not counted in as far as the atomic mass is concerned is they are over 1,000 times smaller than a proton or a neutron. So because they're so much smaller, they don't actually significantly add up to the mass of the atom. So next we have what we call nuclear symbol notation. Once again, this should be review for most of you, is that nuclear symbol notation refers to how you represent different isotopes. It's a second way. So before we called it helium-4 or helium-3, but another way of distinguishing between these is you can actually write it this way, where you identify the number of protons and you put it here. And you write the chemical symbol that matches. These two things must always match. You can't have 2 and then hydrogen. It doesn't work that way. Those two things have to match. Now, once you've matched them, this number right here refers to the atomic mass, or the number of protons and the number of neutrons that are there. Now, the nice thing about the nuclear symbol notation is it actually leaves room for you to fill in right here if there's a charge. You could have this. So you could have helium. It's got 2 protons and 1 neutron in the nucleus, and then it's missing 2 electrons, so it's an ion. That's one of the nice things about nuclear symbol notation, is that you can include everything. From this right here, you should be able to tell me the number of protons, neutrons, and electrons in a particular atom. One of the things that kind of comes out of isotopes is that different atoms, or different atoms of the same element have different masses. And that's what you see right here for hydrogen. Now hydrogen, 1 proton, 1 electron, 1 proton, 1 neutron, 1 electron, 1 proton, 2 neutrons, 1 electron. Those are all hydrogens. Now they're all different isotopes of hydrogen. This first one we just call hydrogen for the most part. This one is called deuterium. The reason why it's called deuterium is there are 2 for the atomic mass. This is called tritium because of 3 for the atomic mass. But there are different isotopes of hydrogen. So the question is what is the number that's reported on the periodic table? And so what you do in order to calculate that number that's on the periodic table, that number refers to the average atomic mass. Whenever you're talking about the average atomic mass, you have to do what's called a weighted average, just like we do for your grades. Test grades are worth 70%, and daily work is worth 30%. So if you get 100 and a 0, you don't get a 50, which would be the average between the two. Instead, you would get a 30 because it's a weighted average. How you calculate for a weighted average is you take the atomic mass and the percent abundance. You have to convert the percent abundance into a decimal by moving the decimal over 2 or by dividing by 100. Once you do that, you multiply the atomic mass and the percent abundance together. When you do that, you get a number for each one of these, which then add up to the average atomic mass. And it takes some practice for you to be able to do this, but it's something that you need to be able to do, and be able to do relatively quickly. Now, one of the most important things about this is you need to remember significant figures whenever you're doing percent abundance calculations. You cannot report data that is more accurate than you are able to measure. More precise than you are able to measure. So you see that here. This is an average for all isotopes of the element. You change it to a decimal, you multiply it across, change it to a decimal, multiply it across, change it to a decimal, and multiply it across. Now, once you see this, okay, this remember is in scientific notation, you see that the average atomic mass for hydrogen is almost the exact same thing as it is for regular hydrogen. Okay, the reason why is 99.98% of all hydrogens are going to be that particular isotope. But it is different, and so you need to be aware of the contribution of each isotope to the average atomic mass. Now, you have example C1. It says a particular mass spectrometer ionizes a sample to a stable form and then separates the components with different mass to charge ratios. Would a mass spectrometer be capable of separating the substances below? Now, if you look at this, calcium is in group 2 of the periodic table, which means that it has a charge of +2. Sodium is in group 1 and has a charge of +1. So if I was looking at the mass to charge ratio, what I would do is I would take the mass of this particular substance, which in this case is 40, and I would divide it by the charge. and I would get 20. Well, if I do the same thing for sodium, 20 divided by plus 1 is 20. These two things are the same. So because they're the same, a mass spectrometer would be incapable of telling the difference between calcium and sodium because they have the same mass to charge ratios. So these are the types of questions you're going to get on an AP. It's not going to be how many protons does calcium have. It's going to be questions like how are these things different, or how can they be the same. So you need to really understand kind of what we're talking about when we talk about nuclear symbol notation so that you can apply it in a situation that you've never seen before. Next one, it says use the data below to determine the average atomic mass for iron. And this one we're going to go ahead and show you how to do, and then after I show you how to do it, I'll let you finish the calculation and see if you match the answer. Remember, when you're doing percent abundance, you need to take these values and you need to divide them by 100. When you do that, this becomes 0.05845. You then multiply across, and when I multiply across for the first one, I get 3.152. The reason why I stop at 3.152 is this right here has 4 significant figures. So I can't take all of these significant figures because this one only has 4. I would do the exact same thing for the rest of the data points, and then I would combine them once again using significant figures to ensure that I have the proper answer. You should get an answer of 55.682 grams per mole, but please make sure that you can do this calculation before coming to class. Next, it says the average atomic mass of chlorine is determined to be 35.45 when accounting for the 2 naturally occurring isotopes. The 2 naturally occurring isotopes are shown below. What is the percent abundance of each? Now, this is a little bit different. It's actually asking you to work backwards. So when you have percent abundance, and you have to work backwards. So I don't know the percent abundance, but I do know that the total of the percent abundance needs to be 100%. So if this was 40, then this would have to be 60. If this was 30, this would have to be 70, and so on and so on and so on. So what that allows me to do is it allows me to write an algebraic expression. I don't know what the value of 35 is, so I'm going to refer to it as x. And I don't know what the value of 37 is, but I can write it as 100% minus x, or more commonly you see it as 1 minus x, because remember 100% is just really 1. So at this point, you can multiply these things across and then add them together. Now when you add them together, you're supposed to get the average atomic mass. And in this case, the average atomic mass is given to you. So you can actually write this thing out and you can say it's 35.45 equals 34.96885272 x plus 1 minus x 36.965, and I'm not going to write the rest. So what you would see at this point is that you would have to distribute this to both terms, and once you distribute that to both terms, you'd have to solve for x. Turns out when you solve for x in this case, if you do it correctly, and please do the math to make sure you can do it correctly, chlorine 35 represents 75.82%, and chlorine 37 represents 24.18%. The last question that we have is an example of a mastery question. It uses something called mass spectrum data. So once again, we've already talked about a mass spectrometer and kind of what it does. This is actually a readout for a mass spectrometer, and it gives you what's called the relative abundance. So it says I'm shooting this many particles out of it. Out of this many particles, this is the ratio that I found for each one of these. Now this question says a sample of unknown halogen. Okay, that automatically narrows our what this could possibly be. Now, how would I know it's a halogen? I did some sort of test on the experimental properties and I've determined this thing's a halogen. Since it's a halogen, it has to be fluorine, chlorine, bromine, iodine, something like that. Now, if you look at the data, you have what is called the mass to charge ratio. So this is saying that I have a 70 to 1 charge. This is saying that I have a 72 to 1 charge, and this is saying that I have a 74 to 1 charge. Now, you may be saying, well, that's three separate things, except for the fact that you're forgetting about isotopes. Now, if you were to look at each one of these things, I think fluorine's like 19, and chlorine is 35.5 roughly, and bromine is, I don't remember what bromine is, but if you look at it, there's a very, very distinct pattern that's here. And it takes some getting used to try and find these patterns. But if you look at it, you have 70, 72, and 74. Now, that's a pretty interesting spread that you have there. Now, if you were to look at it, that means you have something that looks like chlorine 35 bonded to chlorine 35. And if you did that, what you would have is you would have 70. Now, in the previous example, we showed that the vast majority of chlorine is chlorine 35. But we said there was also a chlorine 37. Well, if you have chlorine 35 bond with chlorine 37, you would get 72. And if you have chlorine 37 bond with chlorine 37, which would be a rare occurrence, you would get 74. So this element that we found in the sample is chlorine, but now it wants us to figure out the percent abundance of each. So once we've identified it as chlorine, you have to look at the total parts. Okay, so if you were to look at it, if I were to look at this first sample, I would say 9 out of 16 are chlorine 35, because every one in this sample is a chlorine 35. Now from here, what I'm saying is that out of these 6, 3 of the 16 are chlorine 35. The reason why it's half is this is a situation in which you have a half chlorine 35 and a half chlorine 37. So one of these is chlorine 35, the rest is chlorine 37. And then here there are no chlorine 35s. So what we can say is that 12 out of 16, or 75%, represent chlorine 35. And if you look and you compare that data to what we just had, it matches up almost perfectly. So once again, this is a mastery question. This is as hard as it gets because it's asking you to apply what you know to a situation that you've never seen before. It's not impossible, but it's something you really have to think very, very deeply about. Now, AP questions tend to not be as far out there in the sense that you've seen everything before, but they tend to be based on experimental data, so you've got to get used to that. So far we talked about the rules for naming ionic compounds, but there are several other different types of compounds we need to be able to name as well. And we need to get the naming out of the way as early as possible so you can start to see how it comes about in questions. So the next one we have is naming covalent compounds, and this is once again review from first year chemistry. It says we usually identify which element goes first, usually left to right. So generally speaking, you have hydrogen, or you have carbon, then nitrogen, then oxygen, and so forth. The only difference is the position of hydrogen. Now hydrogen is going to actually be kind of in between oxygen and fluorine. We'll show you exactly where it is in class, but hydrogen's got kind of a funny place that kind of moves around a little bit, but it's really the only other one that's different. We're going to use prefixes for both elements, but omit mono if it's the first element. So we never say monocarbon or dioxide. Okay, we always omit the mono if it's on the first one. Now, if it's in the second element, it has to be there. It's got to be carbon monoxide, not just carbon oxide. And then also, we do not change the suffix to "ide" as you did with ion. So you only do this for the second element, dioxide, trioxide, but you do not do it for the first one. Okay, so once again, it's the whole idea of the cation for ionic compounds was the element. It's the same basic thing. You're going to have an element, and then you're going to have the suffix for "ide," but it's only going to go on the second one. So it's not going to be carbide dioxide. It's just going to be carbon dioxide. So write a chemical formula for the following. It says tetraphosphorus pentoxide. So if I have phosphorus, phosphorus is a P, and oxide is oxygen is an O. So tetra is 4, penta is 5. The next one we go is we talk about trichlorine hexafluoride. So chlorine is Cl, fluoride is F, tri is 3, hexa is 6. When you talk about sulfur, we talk about bromide. This is hepta. Hepta is another word for 7. Octa is 8. So you have 7 sulfurs and 8 bromines. So you need to be able to go back and forth between the chemical formula and the name and the chemical formula for covalent compounds as well. And that's what you see here. It says name the following. Now, if you say water, technically that's correct, but it's really dihydrogen monoxide. This right here, you have hexa sulfur octahydride. And then finally you have carbon tetrafluoride. When we name acids and bases, it's very similar to naming ionic compounds. So this is kind of a review. The difference is, though, instead of having an 8, like if you say sodium carbonate, when you're talking about an acid like or an acid that's like hydrogen carbonate, instead of saying the 8, you replace it with ic. So instead of it being carbonate acid, you would change it to carbonic acid. And that's where you have ic gives 8 or 8 gives ic. It gives us. So anytime you see something like chlorite, it becomes chlorous acid. And then finally, if you had an ide before, like if you had an element by itself, like sulfide, the ide becomes hydro something ic. So it would be hydrosulfuric acid. Other than that, you would name it just like you would any sort of ionic compound. So if you see something that's like H3PO4, it looks like it's an ionic compound, but when you recognize that it's an acid because of the H, what you would do is you'd say, okay, well, if it's an acid, that means that it's going to be, this is phosphate. We've got to replace the 8 and put ic, so it would be phosphoric acid. Okay, bases are treated exactly the same. If you have something that's like LiOH, it's lithium hydroxide. So we see some examples. This is name the following compounds. This right here is bromide. So whenever we do it, an ide, remember, goes to hydroic. So this would be hydrobromic acid. This would be lithium hydroxide. This right here is going to be sulfite. So since it's sulfite, it'd be sulfurous acid. This one we just did, it was going to be phosphoric acid. And then this right here is copper hydroxide. But once again, once you know that copper is a transition metal, you need to specify the charge, and to be copper 2 hydroxide, because there are 2 charges right there. So this is the chemical formula for the following acids and bases. This is hydrosulfuric acid. Hydrosulfuric means that it has to be an S that's by itself. And in that case, you know the charge is a 2 minus, so you're going to have 2 hydrogens to balance it out. For barium hydroxide, BaOH, but you know the charge is +2 here, the charge is -1 here, so you're going to need to put a 2 right there in order to balance the charges out. For nitric acid, you'll be looking at ic, so that means it's the nitrate, and then you would put an H in front of it because NO3 just has a charge of -1, and you just need 1 H to balance it out. When you look at iron 3 hydroxide, you have iron, it's a +3 because of the Roman numerals. Hydroxide, which has a charge of -1. So you would need 3 hydroxide to balance out the 3 of the iron. And phosphorus acid, the us means you're talking about phosphite. Phosphite is PO3, and the charge is -3. So you would need to make it H3PO3. Okay, this is going to take some practice, and you'll start to get used to it as you go through the year, but you need to be able to name and write chemical formulas for all of these. And the last one, we've covered all of these so far in first year chemistry. The last one, the only one that's really new this particular thing, is naming organic compounds. Whenever you're talking about an organic compound, it refers to a compound that contains carbon. Okay, specifically carbon is like the main element of it. Whenever we're talking about organic compounds, they tend to have carbons, hydrogens, and oxygens as the main components. Okay, so if you were to look at it, it has a special naming structure. Instead of it 1 being mono and 2 being di and those sorts of things, If it has one carbon, it's referred to as methyl. And then ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, and decyl. Okay, that's how you're going to name these organic compounds, and it's based on the number of carbons that are present. So if you look at then you have to name the suffix. And the suffix is determined by the functional groups. Now we're only going to look at 3 functional groups at this time, and the 3 functional groups we're going to look at are alkanes, alkenes, and alkynes. Okay, alkenes, alkenes, and alkynes. An alkane is something that contains only single bonds. So you see something like a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, and then there's hydrogens all over the place. Okay, there's hydrogens, but there's only single bonds. Now, an alkene is where you have a double bond. If you have at least one double bond, it changes from an alkane to an alkene. And then the last one is when you have a triple bond. And if you have at least one triple bond, it changes to an alkyne. So what we're going to do is show you how to name a structure, and then you can actually tell it really easy from the formula. Okay, if you have, and this should say alkynes right here. Okay, if the alkanes, if you look at the carbon and the hydrogen ratios, if your hydrogens are 2 times the carbons plus 2, it's an alkane. And the reason for that is if you were to look at an organic compound, something like this, okay, if you were to look at it as something like this, CH2, 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 CH3, the N carbons have an extra hydrogen. That's the extra 1, 2. And then every other carbon has 2 hydrogens attached to it. So if it follows the formula H equals 2C plus 2, it's an alkane. If it follows the formula H equals 2C, that means that it has to be an alkene. Because if I put a double bond here, I need to take away one of these hydrogens and take away one of these hydrogens. Okay, and finally you have an alkyne, which is if you have a triple bond, you need to take away even 2 more. So I would take this away and put a triple bond there. So depending on the ratio of carbons and hydrogens, you can easily name it as an alkene, an alkane, or an alkyne. The last thing we need to do is cover some examples. Now there are some typos on your PowerPoint, so you need to go ahead and change these to this, where it's C6H10 and C4H8. Now if you do that, we can look at the difference between carbons and hydrogens to determine what it's going to be. So the first thing we do is we look at C6, and that lets us know it's going to be hexyl something. Okay, and then we also have C4, which let us know it's going to be, if you go back to your original screen, 4 is going to be butyl, which is one of the ones that's different. Methyl, ethyl, propyl, butyl. So whenever we look at butyl, now we need to figure out if it's going to be an ane, an ene, or an ine. Okay, so the first thing we do is we look at the ratio. We say, okay, if I do carbon times 2, I get 12. And then I have a choice of plus 2, just 12, or minus 2, which would be 14, 12, or 10. Now if you look, I have 10. So because I have 10, that means it's the minus 2 one, which means it's going to be an ine. So the name for this one is hexyne. Now when I look at this, I've got C4. So C4, 2 times 4 is 8. And I can either do 8 plus 2, which would be 10, 8 plus 0, which would be 8, or 8 minus 2, which would be 6. And if you look, I have 8 hydrogens, which is right here. Remember, the middle one is ene, so this would be butene. Now if we get another example, it says write the chemical formula for the following. It says butane. So we go methyl, ethyl, propyl, butyl, which means that there has to be 4 carbons because of the butes. Now it says ane. Ane means it's going to be 4 times 2 plus 2. The plus 2 comes from the ane. So I know that this thing is going to be H10. Now the next one is octyne. The oct lets me know it's going to have 8 carbons. And then the ine lets me know it's going to be 8 times 2 minus 2. So instead of it's going to be H14. Now this last question is a mastery level question. It actually requires that you know just a little bit of information. Whenever you name an organic compound, you actually just take the longest carbon chain, and that becomes the base for the name. So if you look at it, the longest carbon chain we have, in other words, the longest row of connected carbons, is either this or this. They are the same length in terms of chains, but I can't name all of the carbons in this particular thing. I can't say 1, 2, 3, 4, 5, 6, 7, it's heptyl. Can't do that. Okay, instead you have to name the number of carbons that are in a continuous chain. So if you look, I have 1, 2, 3, 4, 5, 6. So it's going to be a hexane. Yeah, I know it's ane because 3, 5, 7, 10, 14. So I have this C6H14, and that's the 2 times 2, or excuse me, 2 times 6 plus 2. So I know it's going to be an ane. And then you may ask yourself, well, wait a second, what about this? This thing is an hexane because it has another carbon that's attached to it. And if you say that, you're absolutely correct. It doesn't have an actual, it is missing something. And what it's missing is the fact that this right here, this connection right here, is connected to the number 2 carbon. You say 1, 2, 3, 4, and how do I know it's 1, 2, 3, 4, 5, 6 instead of 1, 2, 3, 4, 5, 6? You always want to connect this thing to the lowest number possible. So even though you could name it 1, 2, 3, 4, 5, that's not as low as 1, 2. So what I would do is I would refer to this as 2, and then I have to name what it is, and then hexane. Now remember that you have 1 carbon right here. So since you have 1 carbon, it'd be 2-methyl hexane, and that would be the name for this. Now this is a mastery question because it requires you to know methyl, it requires you to know hexane, it requires you to number the carbons, and it requires you to kind of put all that together. So this is a tough question, and this is not a question I would ask you without going over the naming rules first. But you can say, hey, what if instead of this was, if this was CH2 CH3, how would the name change? Well, if this was CH2 CH3, you would have a longer carbon chain, and it would change the entire name of the structure. So we'll go over that again in class, but this is the end of this particular PowerPoint series. Please make sure you've taken your notes and you're ready to turn them in when you begin class, and we will go over some of the key information in class as well.